course in molecules in motion. Today we are going to be having our fourth lecture, that is again on kinetic theory of gases. We will briefly go through whatever we discussed in the previous class, so that we have a continuity. What we were talking about in the last class was the theorem of equipartition of energy. In this, what we had talked about how the internal energy is distributed. Internal energy is distributed in the three forms. One is the kinetic energy of the motion of the molecule, where we talk about the motion of the center of the mass, and the internal potential energy because of the intermolecular forces, or the potential energy associated with the intramolecular forces. Usually what we had talked about in the last class, and I could not show you the figure, was this is the potential energy diagram which I was talking about, when the attractive forces are dominant and when the repulsive force is dominant, and which is the condition where you have the minimum energy of potential. So, this is the potential energy curve of a typical hydrogen atom. So, if we can go through the previous slides, the repulsive forces are supposed to be contributing to the intermolecular forces when the separation of the molecules are small, and the attractive forces are going to be when the intermolecular forces are large. So, this is how we had seen in the potential energy diagram. How we are talking about the internal energy, the potential energy being in the repulsive mode or in the attractive mode. And then we had seen that at low temperature the average kinetic energy is small, and the internal energy is supposed to be corresponding to a bound state, where the internal energy is supposed to be negative. When at higher temperature the average kinetic energy of the molecules are high, so the internal energy is going to be positive, and this is going to lead to the molecules having enough energy to escape the intermolecular forces to become a gas. And what we were talking about in the last one was the minimum potential energy at the point which we are looking here. This is the point where we can consider the atom as behaving like a spring. So, this is what we had talked about in the last class. We had talked about what was the degree of freedom. In a dynamic system, the number of directions in which a molecule can freely move, or you can say the coordinates, minimum coordinates required to specify their spatial presence in a particular position in the space or the configuration of the system, is what is known as the degree of freedom. And how the energy is distributed in the degrees of freedom will be depending on the type of molecule we are talking about. If we have a monoatomic molecule, or we have a complex, if more than one atom involved, we have diatomic molecule, we had treated that as a complex molecule and discussed in the last class. What we had done in the assumptions was, the first assumption was how the internal energy is distributed among the n number of gas molecules, and what we had talked about was each independent degree of freedom has an equal amount of energy of half kT, and kT is actually the kb, that is a Boltzmann constant. We usually say while talking, we are talking, and instead of saying kb, we all may say kT also. So, this is the basis of the equipartition of energy, and based on that we are going to be moving into a new another concept, which is going to be derived from whatever we have discussed in the equipartition theorem. The equipartition theorem essentially talks about each degree of freedom contributes half kT to the energy of the system, wherever the degree of freedom is in addition to the associated with the translational or rotational or vibration motion of the molecule. So, this we had talked about in the last class. So, what we are going to do today, this is also something which we had discussed in the last class, how the internal energy can be actually, for a monoatomic gas, can be the total translational energy, because it is a monoatomic gas. We have a point atom or a point mass, where we do only associate with the translation motion, we do not have any other motion associated with it. So, the total internal energy is going to be the measure of the total translational kinetic energy of the system. So, that was as we had if you remember, it was taken to be 3 by 2 n kBt, n being the total number of molecules, monoatomic molecules involved in the system. So, this was what we had talked about, and how internal energy was a function of temperature, and how that can be equated to the say specific heat. We had talked about in the last class, but we will not go into details of it. Today we are going to look into another concept, which is the root mean square speeds of molecule. I again revise, because root mean square is a term which is very important when we are talking about kinetic energy, and I want you people to understand what I am talking about. See, velocity is a vector quantity. Suppose I have a mass m and that is moving with the velocity v. So, it will have, since it is a spatial x y three coordinates are there in space x y z. So, if I say that the velocity is v x along the I axis and along the x axis, v y along the y axis, and v z along the z axis. And here what I am considering, the molecules, the collisions of the molecules, if it is happening on the right hand side of the container, then the orientation which is going to, what we are looking into, is a unit normal vector. Unit normal vector, if I am talking about right hand side, I am talking about the x axis, then the unit normal vector pointing on towards the container is going to be the positive I direction. So, this is the I factor which is associated with the vector. So, since it is an elastic collision which we are talking about, so if I am talking about the direction only x, then I will consider that the z and y axis components are remaining unchanged. But the concept is that the molecules are going to be probably oriented everywhere, not only in x axis, y axis as well as z axis. When I am talking about the collision along the right hand side, where I have the unit normal vector as I, positive I, then I am talking about a positive x direction. Now, similarly, if I talk about the symmetry, because it is equally probable that you have the molecules in the x and y and z axis. So, what I can say, the average square of the x and the velocities in the x component, the y component and the z component can be given as something like this: V x square v equal to V z V y square equal to V z square. This average energy along the x y z direction, that is going to be equally probable, and they should be equal, because we are talking about in terms of the symmetry, because they are all equally probable in the x y z direction. So, the average square can be given as the average of this is equal to the sum of the average of the squares of the components. So, I can write down the sum of the squares of the component, and this is since these are all equally probable. So, I can write down this in terms of x, y or z. I can write down 3x as the average velocity square is 3x in the x direction, or I can say that average along the x axis 1 by 3, whatever the term which I have taken. This was actually derived from the Pythagoras theorem, if you remember in the previous classes we talked about 1 by 3. This velocity square is what we are talking about, is the root mean square, and this sometimes is referred to as C in some of the textbook. So, please do not confuse, this is actually the average velocities which we are looking into, but we are saying this is as root mean square velocity, because we are going to be taking the exact meaning of the term. We are going to take the under root of the mean of the squares of the velocities of the molecules. So, this is how we are going to define the RMS velocity, and if according to the previous derivations which we had carried out, the key results of the kinetic model was the pressure volume of the gas could be related by this expression. I am not going to read out the expression, it is obviously visible to you. PV equal to 1 by 3 Nm into this C is the root mean square velocity I am talking about. This is also the root mean square velocity. Again, this is related to the Kb of the Boltzmann constant to temperature. So, we can see that pressure is directly proportional to the root mean square velocity. The root mean square velocity C of the molecule depends on the temperature. From this expression, if we can equate, then we can see that the root mean square velocity is directly dependent on the temperature, and if the temperature is constant, then from this expression we can say PV, if you multiply and temperature is a constant, then for a n number of molecules in a system, the PV becomes a constant. So, that is something which is the Boyle's law. We are going to discuss that the verifications of the gas laws a while from now. So, again, if I have the PV equation and I say that equation can be equivalent or can be equated to a equation of state of a perfect gas, that is PV equal to nRT, then this part PV should be equal to nRT. So, that is how I equated this. This is also PV. So, I equated to nRT. From there, what I am trying to find out is the root means expression for the root mean square velocity. Root mean square velocity is equal to, is going to be given by, from here you can understand, it is going to be nRT divided by m into capital N into in the numerator you have the 3. So, what you are doing here, you just see what you are putting, you are substituting for n, the number of moles is going to be total number of molecules by the Avogadro number, and you know that small mass, that is the mass of the gas, into the Avogadro number gives you the molar mass of the system. So, if you substitute this in place of the m, then you get the expression. This is the expression of root mean square velocity. So, what is this root mean square velocity? From the expression, it is clear that it is going to be directly proportional to the temperature, and it is inversely proportional to directly proportional to under root of temperature, and it is inversely proportional to under root of the molar mass. So, the higher the temperature will be, you will get the higher value of the RMS, the root mean squared speed of the molecule. For a given temperature, that means if you, since it is the RMS velocity is inversely proportional to the mass. So, the heavier the molecule will be, slower that movement of the particle will be, because the molar mass will be higher. So, it is, since it is inversely proportional, so the speed will be lower. So, heavier molecules will move slowly compared to the lighter ones. Again, one important factor is sound waves are pressure waves. Okay. So, these propagate, as they propagate, the molecules of the gas must move from a higher pressure region to a lower pressure region. So, since it is propagating through the air, so we can say that the RMS speed of the molecules of air is expected to be comparable to the speed of sound in air, that is around 340 meters per second. Now, again, if you see the expressions, expression of the root mean square velocity, you will see that if you hold the temperature constant for a system, if you have two type of gases, if you hold the system at the same temperature, then you will see the ratios of the RMS velocities will be inversely proportional to the under root of the masses. So, if you see here, if you have helium, the RMS velocity of helium and RMS velocity of neon, if you can take the ratios, it will be under root of the molar mass of neon divided by the molar mass of the helium. So, these are things which is important when you are talking doing calculations or numericals. So, another factor which needs to be remembered, we have this expression of pressure. So, you will see from in the expression of the RMS speed, we do not have a term of pressure. So, RMS speed of a gas molecule is independent of the pressure. If the temperature is held constant, then the molecules, the gas molecules are independent of the pressure of the gas. If you see the expression of the pressure, what you see is pressure is directly proportional to the N by V. What is N by V? It is the number of molecules per unit volume of the gas, that is the container which we are talking about, this V. So, this is the number density. Similarly, if you can see in the expression you have m, small m, it is the number of molecule, the mass of the gas. So, mass of the gas divided by the total volume will give you the density. So, as the number density or the density of the gas increases, what happens? The pressure increases, but it does not have any effect on the RMS speed of the molecules. They remain unchanged. Now, let us see one example. This is a solved example for finding out the RMS speed. RMS speed is the expression which we have here is 3 RT by m. So, if you want to find out the RMS speed for n nitrogen molecules at 300 degree Kelvin, then you can put the values here. As you see, 3 into, you put the values, the gas constant 8.31 4 joules to the Kelvin inverse, mole inverse into the temperature, which is in Kelvin. And here you remember you have to convert the molar mass into kgs per mole, because you have in joules. Joules is 1 joule is what is given by Newton meter, and that is, if you convert that into kilo meters per second square, that will be again into multiplied by m. So, if you see, the kgs will get cancelled. So, what you are left with, meter square per second square. So, if you take the under root of that, you get by the units of meters per second. So, this is one of the solved examples you can see for finding out the root mean square speed of nitrogen molecule. So, why do we take the root mean square velocities? Why can't we just take the average velocities? See, why can't we take average velocities? When, see, the molecules are moving along the x axis, y axis and z axis. We are looking into the movement of the molecules along the 3 axes. So, it is not just the x axis, but it is on the positive x axis and the negative x axis. Since the according to the symmetry rule, it is possible that all the molecules are going to be equally likely to move in the x plus direction and in the x minus direction. So, what if, even if you take the mean, what happens? You add up coming to 0, because minus velocity and plus velocities will eventually come to giving you a total average of 0. So, that is the reason we do not take the mean velocities, but we go for taking the root mean square velocity, and the name itself suggests what the root mean square velocity is. It is the square root of the mean of the squares of the velocities. So, what is the difference between having a RMS speed and the average speed? Why do we take it? Let us see an example out here. Suppose you have 4 molecules of gas moving with the speed minus 1 meters per second, plus 1 meters per second, minus 2 meters per second, plus 2 meters per second. So, if we want to find out the average speed of this molecule, since these are vector quantities and they have positive and negative terms, we have to first convert these 4 vectors into a scalar component to find the speed. So, that we can do that by removing the signs. So, if you remove the signs, what you are doing after doing the conversion, you get all the positive terms. You remove the signs to get the scalar quantity of speed. Instead of talking about velocity, we are talking about speed now. So, the average speed will be what? We add all the speed values, 1 plus 2 plus 1 plus 2 divided by 4, then total number of molecules, you get 1.5 meters per second. Now, on the other hand, how do you find out the root mean square velocities? Here we do not need to convert the vectors to scalars, because you have the square terms as soon because we are taking this mean of the squares. So, we are squaring each term. So, the negative terms will be automatically becoming positive. We do not need to look into the conversion of a vector to scalar. So, that is the reason why we use RMS speed. So, minus 1 square plus 1 square minus 2 square. So, it becomes 10 divided by 4, you take under root, you get 1.5. Now, you see, if you take the RMS speed and the average speed, if you are calculating by converting these vectors into the scalar quantity, in spite of that, you will see that the RMS speed is 1.58 and here it is 1.5. So, the RMS speed is going to be higher and then the average speed, and they are not equal. So, the root mean square speed is not exactly equal to the average speed, and that is why we always concentrate on the RMS speed, because we are dealing actually with the vector species of velocity. Now, today we are going to be looking into some of the terms which we have dealt in the beginning. We have talked about the gas laws. Now, we will do the verification of gas law based on whatever we have found from the kinetic molecular theory of gases. So, what usually the kinetic molecular theory is in various books you will find that it is abbreviated as KMT model of gas. So, now we are going to account of the whatever we have observed in our kinetic model. Is it going to be valid for the gas equations which we said is going to be should be valid according to our findings. So, what we talk about? We talk about pressure and volume conditions first. If the temperature and the number of moles of the gas is held constant, the temperature and the number of moles is held constant, then according to Boyle's law, we know the pressure is inversely proportional to the volume, right. This is going to be the expression of inert gas law. If the temperature is held constant and the number of moles are held constant, this part is constant. So, pressure is going to be inversely proportional to the volume. Now, how does the kinetic theory justify this? When you have a volume of the gas reduced, what happens when you reduce the volume of the gas from here to here? What happens is the space you are providing for the molecules to move is confined further. So, there is the number of collisions which is going to be taking place, the frequency of the collisions which is going to take place with the walls of the container is going to increase. And what is pressure? Pressure is that is proportional to the number of the collisions the gas molecules are making on the surface. So, when you are reducing the volume, then what is likely? The number of the frequency of the collisions with the walls are likely to increase. What will it give rise to? It will give rise to the increase in pressure. So, according to the kinetic theory of gases, if you are decreasing the volume of the gas, then the pressure of the gas is supposed to rise because of the increasing number of collisions with the vessel surface, okay, container surface. So, that is nothing but the Boyle's law. So, we have proved one of the gas laws, and the next one is, suppose the number of moles and the volume is held constant. Then what happens? The pressure is directly proportional to the temperature. This is the Gay-Lussac's law. Gay-Lussac's law says pressure is directly proportional to temperature. Now, what happens through the kinetic model? Do we justify what we have got through the gas law model? Now, what we have? We have number of moles fixed, we have volume fixed. We are not changing the volume. Now, I increase the temperature by heating, supplying some amount of heat to the container. What happens as you rise the temperature? What happens? The velocity of the gases will increase, because the temperature is direct measure of the kinetic energy. So, the kinetic energy is increasing, so the speed of the molecules is going to increase, the velocity of the molecules are going to increase, and so will be the frequency of the collision with the walls. So, as you increase the temperature, the frequency of the collisions with the wall also increases, because now the speed of the molecule has increased, they are moving much faster. So, the rate of collision with the walls is going to be increasing. So, the frequency of collision is increasing, and if, the impact which is we get from the collision is actually the measure of the pressure. So, the pressure is going to rise. So, what we had got from the Gay-Lussac's law as pressure being directly proportional to temperature is what we are going to see in this kinetic model as well. Now, the next one is the Charles law. What does the Charles law say? Number of moles are held constant, the substance is constant and the pressure of the gas is held constant. So, pressure is held constant, number of moles are held constant. What we see is Charles' law. According to Charles, the volume is going to be proportional to the temperature. Now, what we are doing here, we are taking the number of moles and the pressure as constant. So, if I have a weight, I have equal weights on the surface top, that means the pressure I am trying to maintain as constant, which is pressing the gas. So, the pressure maintained constant if I start heating the gas container. So, what happens, the gas will increase in kinetic energy, they will be moving much faster. So, they will start hitting the walls of the container much faster, the frequency of collisions will be much faster. So, under that condition, what you have the increase in pressure, but we are having a condition where we want to maintain the pressure constant. So, to maintain the pressure constant, what we have to do, we have to expand the gas, right. So, the gas expands and you have a increase in volume. So, as we increase the temperature, we actually need to increase the volume of the gas to keep the temperature constant for a fixed amount of gas. This is the Charles' law, and then we have the Avogadro's law. Avogadro's law, what does it say? If the pressure and temperature of a gas is held constant, then according to Avogadro's law, the volume of the gas is proportional to the number of moles of the gas. Okay. So, suppose I have a gas container where I have the pressure of each of the gas being constant. Now, what I do, I have a separate external gas cylinder supply. I attach the gas molecules, the cylinder to the container and pass the gas molecule. Now, I am supplying the increased number of moles. If I am increasing the number of moles, what happens? It is going into this. With increasing number of moles of the gas, and we are holding the pressure, trying to hold the pressure constant, what is going to be happening? The number of collisions are going to increase. So, the pressure is supposed to be increasing, but we are keeping the pressure constant. Though to maintain the pressure constant, what we have to do? We have to expand the gas. So, if we are increasing the number of molecules or number of moles of the gas, but you have the conditions of constant pressure, then the volume of the gas should be proportional to the number of moles. This is also verified by the kinetic model. Then the last one is the verification of ideal gas law, which is the Dalton's partial pressure law. Dalton's partial pressure law states the total pressure exerted by a mixture of non-reacting gases is equal to the sum of the partial pressure of the individual gases. So, what I have, I suppose have two types of gases, one corresponding of blue colored balls and the other red colored balls. What happens? The pressure exerted by each, what is going to be the pressure exerted by this is going to be nRT by V. Okay. Here nRT is the number of moles for the blue balls, here it is the nRT for the number of red balls. So, what I have, the total pressure will be, since they are not reacting, according to the kinetic model, we do not have interaction between the molecules. So, what happens, the total pressure is now going to be the partial pressure of the blue system as well as the red system. When we mix these two, they are not reacting gases. So, they will behave as if the two different gases are introduced in the same container, it will each behave like the other is not there. The partial pressure of the gas is as if only one gas is existing, the other is not existing at all. So, they are not dependent on the other gas. So, each gas exerts a partial pressure independent of each other. The sum of the partial pressures, if I take the sum of the partial pressures, this is, and I can take the number of RT by V as common, and then what I get is the number of moles of the blue and the number of moles of the red. So, what I get is the expression of Dalton's pressure, partial pressure, law of partial pressure, that is P equal to total pressure equal to RT by V summation of the number of moles. So, what we have, the total pressure depends on the total number of moles of the gas particles, and it is independent of the type of the gas which we are talking about. So, the total pressure is going to be the sum of the partial pressures because they are not reacting gases, and according to kinetic theory of gases, the molecules do not have any interaction with each other. So, they are going to be behaving independently. So, if you are talking about a gas pressure here, we are talking about one type of gas pressure contributed by this system, another contributed by this system. So, the total pressure of this system and this system together should be the pressure. So, this is the pressure, partial pressure, which we call a, and this is the partial pressure we call for this system. The total will be the summation of the partial pressures. So, this is what I have discussed. Next class we are going to be talking about the molecular distribution of speed. Thank you so much.